All right. So as a reminder to everyone who's not here and watching, and if you're not here, you better be watching, that even if I generally hand these out in class, everyone is responsible for frequently visiting the course website, where everything has always been posted, including these handouts to keep up with due dates, etc. Okay, and one more. So the handouts for problem sets 9, 10, and 11 are the ones that are going around. Okay. Now, so this two will be on Wednesday in 2 weeks on all of the Chapter 3 stuff. And you can see the practice tests and solution, like the first test. On the lecture page. So there'll be problems, for instance, where you have homogeneous PDEs, the second order PDEs, where there's different cases of roots that are real distinct, or complex roots, or repeated roots. There'll be a question about reduction of order, where you're given a solution and use reduction of order to find a second solution. Let's see. And what we're talking about this week, non-homogeneous equations, like undetermined coefficients, variation of parameters. And then next week, so we're talking about sections 3.1 to 3.7. Now on Monday, I will not be here. The other mathematician in my family, my niece, is getting married, so I have to go to DC for that. So there will be a substitute. Dr. Zhu will be taking over on Monday. So he'll start covering the last section that'll be in the test 3.7, and then I will finish it off on Wednesday, and then there'll be some time for review before test. And then same deal as last time. So Wednesday is when you'll take it, and then you will be given feedback and opportunity to clean up whatever mess you made on that Friday. For a final, it's going to have to be a little different, just because since it's during finals week and there's just no time left. So what I will do in that case is on the last day of class, which is Friday, May 5th, I will give you a chance in some form to start the final, like maybe picking out certain problems or giving you some time to get started on it, and then you. So it works in reverse, because in this case, if you have a whole class period on Wednesday to work on it, and then you'll have part of a class period, a good chunk of it, on Friday. Whereas, well, finally, you have a shorter time up front, and then a longer stretch during finals week. So essentially, yes, it's just done a little differently. Okay. Now, okay, well, maybe had a couple more people come in, but all right. Now, as far as how this relates to assignments, through problem set 12, that is the last problem set that will be featured on the test. And that deals with problems involving springs, and that's what Dr. Jules started covering on Monday. This particular set is not due until after the test, but the material will be covered well before. Okay, and you see there's one problem in a practice test that's on it, and then there'll be some hidden bonus problem. Okay, now to get into the first of the two methods, that you'll be using to solve non-homogeneous second-order equations. So this is method of undetermined coefficients. And this is section 3.5 in the text, but it's 3.6 in the notes. So I'll be working with examples, almost all of which are in the notes. So the way this is going to work is I'm going to pick out an example and step through it, and then I'm going to give you guys one, and then so then you're going to follow the same process that you'll just seen me do, and we're going to do a little back and forth like that for different situations. So, in other words, pay attention, because you're going to be doing this yourself in a few minutes. So the first problem we'll look at is y double prime minus 2y prime minus 3y is equal to, so my g of t on the right side, I'm going to throw in two terms, 3 e to the 2t plus t. Now, when you have a situation where your g of t is a sum of more than one term, the goal here is to find a particular solution that's denoted by y sub p of t. So you can try to find a function yp that satisfies this. Right now, we're not dealing with initial conditions. That will be handled separately. Now, when you're trying to find a particular solution, if g of t, that's this, has more than one term in it, what you're allowed to do is you can find your particular solution for each term separately. And then once you have those handled, then you can just add them together. So that's what I'm going to do, is find a particular solution for this problem where the right side is 3e to the 2t, and then do the same thing for t, and we can just add those. Okay. So then you're not dealing with so many actual undetermined coefficients all at the same time. Okay. Now, to help you organize your thoughts when working at these problems, I'm going to make a little chart for you. And then I'll just go ahead and fill in the chart. So the very first thing you do is you find the, actually I'll back up a little bit. First, what is the homogeneous equation? Then from that, what is the characteristic? Now once you start doing these, like do them on one of the homework sets or practice for a test, you don't have to go for these things. Let's go. For now, more steps is better. But once you get the hang of it, then you can skip certain ones if you feel like it. Well, it's a characteristic equation. Then what are the roots of that characteristic equation? And then, so the roots of that. And then there's a second column of roots. The roots of your g of t. This is what I was talking about last time, about knowing this process forward and backwards. Given certain roots in your characteristic equation, you're supposed to know what kind of solutions those give rise to. For example, if it's real roots, then you have exponentials. If you have complex roots, you have an exponential times the sine and cosine. Things like that. So you need to backtrack from your given g of t to what roots do we correspond to. And then your next column is number of overlaps. In other words, how many times does a root from here appear in a list of roots from here? Often it'll be 0, but sometimes it won't be. Well, it'll be at most 2, because you're only going to have 2 roots over here. And then finally, you have your form of your particular solution. So what kind of function it is, and what's left is certain undetermined coefficients, certain constants that you have to find. And that's where we'll substitute in and find them. Okay, so I'm going to fill in this chart for these two cases. So a homogeneous equation is just the dE that you're given with 0 on the right-hand side. Okay. And then from there you get the characteristic equation. So r squared minus 2r minus 3 is equal to 0. And then you can go ahead and find the roots of this. And certainly this one factors nicely. So r plus 1, r minus 3. So the roots in this case turn out to be minus 1 and 3. Then our g of t, I'll write down the g of t here, is 3e to the 2t. Now what we have here is only an exponential. So what you're doing is you're looking at any exponentials or sines and cosines that you have to determine if they would arise from having real or complex roots. Bless you. Here we only have an exponential. There's no sine and cosine. That tells you you're dealing with a real root. The constant here tells you what the root is. So the root is 2. So we're comparing this root of 2 with these roots over here, minus 1 and 3. Well, there are no matches. So there are no overlaps. So now what is the form of your particular solution? That comes from whatever roots you've got over here for your g of t, and if you have any overlaps, those two are taken into account. So since there are no overlaps, we just focus on this. And what we're going to have is e to the 2t times a constant. So our particular solution is of that form. All right. Any questions so far? I'm going to do another one, but. Okay.
On your g of t, why isn't the t included as well? Like,
Because of what I said here. You can consider each term separately.
Okay.
Now I'm going to use the t. Okay, so now let's go through that. The second one, well, the first few steps will be the same, because we're dealing with the same underlying dE. So I'll skip to here, where we have minus 1 and 3 are roots. So now for g of t equal to t, now what happens here is, like I said, you look for sines and cosines, you look for exponentials. Well, there aren't any. When that happens, if all you have is a polynomial, the root that's involved is 0. Because imaginary parts come from sine and cosine. Non-zero real parts come from exponentials. Right. So once again, we're comparing these. There are no overlaps. Okay. Now, can anyone tell me, if you get 0 as a root, like of your characteristic equation, if I had gotten 0 over here, what kind of solution, what solution does that give? So instead of an exponential or sine and cosine, if the root is 0, what's your solution? All right, you might think 1. Okay, so you might think, okay, maybe my particular solution is 1, or maybe it's a constant. But here's the problem. If I were to plug that in to this equation, because that's the next step, you take this and you plug it into all of this. Well, if you plug in a constant, you're going to get 0 from here, 0 from here. You'll get minus 3 times the constant over here. But if you only have a constant over here, there's no way that you're going to get that to agree with t over here. So that alone is not enough. So what you need to do is be a little more flexible than that. So really the form is a constant, which I'll call a0. Actually, I'm going to call it b, because I have a up here, plus b1t. So, what we'll see, and we'll see this for more examples, is after you figure out what happens as a result of your roots, or these roots, and your overlaps if you have them, and we'll deal with overlaps later. If there's a polynomial involved of a certain degree, you have to allow for a polynomial of the same degree. So for instance, if I had t cubed here, then I would have to have 4 terms here, like b0 plus b1t plus b2t squared plus b3t cubed. I have a general polynomial degree 3. So to get to roots, you're looking at exponential sines and cosines. And that'll be reflected over here. But if there's a polynomial multiplying all of that, then also multiply by a polynomial, arbitrary polynomial of the same degree here. Okay, so now we have, for both cases, a form of a particular solution. And now we can go about determining the coefficients. Oh, God. What happens to these erasers when I'm here? All right. So now you can still consider one term at a time. So with a first example, your particular solution is a constant times e to the 2t. So you need its derivatives. So we have 2a e to the 2t, and then 4a e to the 2t. And now you substitute those into, now we're only focusing on one term of g of t at a time. So you substitute into just 3e to the 2t on the right side. We'll deal with the t later. So we take all this and substitute it in here, and what we get is 4a e to the 2t minus 2 times 2a e to the 2t minus 3a e to the 2t, and that must equal 3 e to the 2t. Now, what's convenient is you have e to the 2t everywhere, in every term on the left side and right side. So go ahead and cancel them out. What else do you have in every term on the right side? No, sorry, left side.
A.
Yeah, go ahead and factor it out. So what's left is 4 minus 3 is equal to 3e to the 2t. So now you have minus 3a is equal to 3e to the 2t. So you conclude that a is minus 1.
What did you say?
Yeah, you said you crossed out the e to the 2t.
Oh.
Why did you cross it out?
Because basically I'm dividing by e to the 2t both sides,
Okay.
just to simplify. Yeah, and then I forgot that I dropped it on the right side. Are we good now? Okay. Do we see how a is minus 1? Okay. So you can conclude that your particular solution is minus e to the 2t. Okay. So now you have your particular solution for that. And then you would add this to the general solution to the homogeneous equation, which you know how to get from several sections back. And there you have your general solution of the whole problem. And then if you have initial conditions, then you use those to figure out the arbitrary constants that are in the homogeneous part of the solution. It's just that now this also is going to be there. That's going to be taken into account. For the other one, so where g of t is just equal to t, and your particular solution is found to have a form b0 plus b1t, you go ahead and find your derivatives. So first derivative will just be b1, and your second derivative will be 0, so that's convenient. So now you substitute all of that into your non-homogeneous dE, y double prime minus 3y prime minus, 2y prime minus 3y is equal to t. So we get 0 minus 2b1 minus 3 times b0 plus b1t, and all of that must be equal to t. Now, when this happens, you have several terms with different powers of t. It's a good idea to combine like powers of t. So first I have minus 3b1t, and then for my linear term, then my constant term is minus 2b1 minus 3b0. And all of that must equal t. So we match powers of t over here with powers of t over here. So the coefficients must all agree. So minus 3b1 must be equal to 1. And then this part, the constant term, must be equal to 0 because there is no constant term on the right side. So now you can just go ahead and solve these. So b1 is minus 1/3. And then you can plug that in down here. So we have 2/3 minus 3b0. Let's move the minus 3b0 over to the right side. So b0 is 2/9. So your particular solution is equal to 2/9 minus 1/3 t. So that plugged into this dE will give you what you're looking for, t. All right, so use the roots of a homogeneous equation, use the form of your g of t to find the form of your particular solution that has some unknown coefficients, plug that into your non-homogeneous dE to figure out what the coefficients must be. Questions?
You said you just picked one, the one, negative 3b, sub 1 equals 1.
Okay. Well, because remember, matching like powers of t.
Okay.
Yeah. So I look at what terms have a t because the coefficients all have to equal. Yeah. Yeah. So the 1 comes from a coefficient of t over here. And actually, so does the 0 because there is no constant term over there.
Can you go over how you got the form of y of t for the second one?
Well, what happens is, all right, because having a root of 0, normally that would give you the particular solution of 1. But that's based on any exponentials or sines and cosines you might have. But if whatever you have is multiplied by any polynomial of whatever degree, you have to allow a polynomial of that degree in a particular solution. So, like for example, I'll go back to this one. Here I only had 3e to the 2t. I only had a constant. So I only have a constant here. But let's suppose I had 3t squared e to the 2t. Then I'd have to have constant plus a linear term plus a quadratic term, all of that times e to the 2t. So any polynomial in your g must lead to a polynomial of the same degree in your particular solution. There'll be more examples that help cement that. And in the notes, there's a chart, also in the textbook. Okay, so what I'm going to do now is,
You said add the results.
yeah, you can add the results together. So, dang, I shouldn't start erasing that. Sorry, I'm just taking way more time than I expected. It always does. Now, okay, so the particular solution of y double prime minus 2y prime minus 3y is equal to 3e to the 2t plus t is the sum of particular solutions over here. Yp of t is equal to minus e to the 2t plus 2 ninths minus 1/3 t. And I can go a little, actually I should go a little further. The general solution of this dE is y of t is a constant times e to the minus t plus another constant e to the 3t, because those are the roots of the homogeneous equation that were written down earlier. So you always have that plus the particular solution. So minus e to the 2t plus 2 ninths minus 1/3 t. So now, if you were given initial conditions, you would apply them to this. So you would, like, suppose you have y of 0 equals something, y prime of 0 equals something. You plug in t equals 0 in all of this, including the particular solution. And then you take the derivative of all of this, including the particular solution, and use that to find your C1 and C2. So the similar process to what you did in homogeneous equations, you just have to include a particular solution in whatever you're doing. Okay, now, I'm going to throw up another dE here. Y double prime plus 4y is equal to t squared plus 3e to the t. Okay, and we have initial conditions. Okay, so similar chart, I'll write it vertically this time. So the homogeneous equation, y double prime plus 4y is equal to 0. The characteristic equation, all right, this time you guys are going to help me. What is the characteristic equation?
R squared
Plus 4y.
Plus 4 is equal to 0. Okay, so what are the roots?
Plus or minus.
Plus or minus 2i. You have complex roots in this case. And certainly that will never be 0 for any real value of r. Okay, now let's focus only on g of t is equal to t squared. What root does that correspond to? What? Remember, exponentials and times of cosines determine roots in certain cases, but if you don't have them, your root is 0. Okay, so you check, is there any overlap between these two? There is no overlap. Okay, so therefore your form of a particular solution, now a root of 0 would normally lead to a constant, but you don't have a constant here, you have t squared. So this gets back to the question that you were asking earlier. Your form of particular solution is a0 plus a1t plus a2t squared. So you're allowing an arbitrary polynomial of degree 2 to be a particular solution. That means you have 3 coefficients to determine. So you substitute this into y double prime plus 4y is equal to t squared. And you're going to get 3 equations for the 3 coefficients. Because what will happen is on the left side, you're going to get some second degree polynomial unknown coefficients. And you're going to group by powers of t. All right. This is on page 60 in the notes. You can see there, so what I'd like you to try to do is go ahead and substitute this in there and see if you work out the coefficients, but you can consult page 60 of the notes to see if you're right. But any questions about where the form comes from? Now, on the other hand, for the other term, g of t is 3e to the t. So what root does that correspond to? 1, because you look at your exponential for a real part of your root, and the coefficient of t is 1. So you get 1. There is no overlap again. So your form is some constant, I'll call it b, times e to the t. So then you can substitute that into y double prime plus 4y equals 3e to the t and figure out your 1 coefficient from that. This is also done on that same page, 60. Because once you have the form, you just take a couple derivatives, and then after that, it is algebra. But well, I want to make absolutely certain that I do. Well, any questions about how we got the forms in here? Because all the examples you've seen so far today have no overlap involved. I need to show you how to handle that. Okay. So for this next example, I have well, going back to a left side of the DE that we had before. But now the right side, the G, is minus 3t e to the minus t. Okay. So if you go through the same process, the roots that come from here are minus 1 and 3. Now, from here, what root gives rise to that kind of solution? Yeah, minus 1. I think someone said double root. That would. So that's we're not thinking those terms here, but the fact that there is agreement now between these is significant. So in other words, when determining what roots are involved, whatever polynomial is in front, set that aside when it comes to determining the roots. We'll work this into it at the end when we're coming up with a form of a solution. So the number of overlaps, we have a minus 1 here and a minus 1 here. So there's 1. So normally, okay. Oh, before we deal with the overlap, does anyone tell me what the form of a solution would be based on what I've shown you already? There's an e to the minus t. What should we put in front of it? How do we account for the t? My hearing sucks. Try again. Constant. I'll call it a0. And what else do I need?
Plus A1, 2.
Yeah, because we have a polynomial of degree 1 here. That means we have a polynomial of degree 1 here also. Okay, so based on what I've shown you before, you think, okay, that's your solution, except that's actually not going to work here because of the overlap. So because we have one overlap, we put in t to the first down here. So you actually always have t raised to a power that's the number of overlaps. But in the other examples, that was 0, so we didn't put anything. So if we had, for instance, we have minus 1 here, and then we had a double root of minus 1 over here, that's 2 overlaps, so we'd have to have a t squared. So that is a form of your particular solution. And what I would suggest before going further is if you have a t out here, go ahead and distribute it. So that's a0t plus a1t squared times e to the minus t. And you substitute into y double prime minus 2y prime minus 3y is equal to minus 3t e to the minus t. Now, the differentiation is going to be a pain in this one because you got to use what? Product rule. Yeah. So this substituted in here where the coefficients a0 and a1 are worked out, you can see that done on page 59 in the notes for all the algebraic details there. Okay. Any questions about the form and how the overlap changes things? Okay. All right. Let's look at another. Okay. 1 double prime plus 4y is equal to 3 sine 2t. Y is 2, y prime is 0, is minus 1. This is on page 61 of the notes. Okay, so we go through the same process. Well, the left side is something that we've seen already. The roots are equal to plus or minus 2i. Okay. Now, the roots for g of t is 3 sine 2t. So what kind of roots would lead to a solution like that? What? I'm sorry, my hearing sucks. Yeah, yes, but which complex root specifically? Yeah, plus or minus 2i. Because of the 2. So the coefficient of t in your sine or cosine gives you the imaginary part of the root, just as the coefficient of t in the exponential gives you the real part. Okay, so the number of overlaps for these purposes is 1. So you have, so you're looking at like either one of the complex roots plus or minus 2i. Either one of these roots appears once as the root of the original equation. So for form, okay. So what do you think the form should be then?
A sine b plus b cosine b.
Okay, so a what?
Sine 2 plus b cosine 2.
Almost. What else do we need?
Times G.
Times t. Yeah, so with no overlap, yes, this is what you'd have. And we multiply all of that by t because of the overlap. Okay. All right. So unfortunately, that's going to lead to the product rule again. Well, first, before we go any further, any questions about the form?
Could you explain to me why it's only one overlap again?
Okay, my crass answer is because that's what works. But the guideline that you follow is you choose. Because what happens is the other cases that we saw where there's real roots involved, each solution was associated with a single real root. Here it's associated with a pair of complex roots, but we just take one of those roots and see how many times it repeats. Because what happens is all of these forms come about from a situation where, like from the solution formulas I have earlier in the notes than this, and you try with certain GTs, and you're always, for a particular solution, you're always working on the integral, and what does the integral actually look like when you grind it out, and we end up with a t and not a t squared. Okay, so, but yeah, I can see how that can lead to a little confusion there. Okay, well, so what would the derivative of this be?
cosine 2t minus, no, 2a cosine
Yeah, figure for the 2 at the end.
minus 6 cosine
6.
6. Oh, I thought that it's 2, sorry.
Okay. Alright. Oh.
Sine 2t.
Okay. Almost gave me an aneurysm there. Okay. Alright. Actually, for something like this, it seems to be what you're doing is it's actually easier if you just think of this as a whole. To keep it together for purposes of applying the product rule. Okay. And then yp double prime. So what will happen is it's going to be very similar down here. And then you have 2a cosine 2t minus 2b sine 2t. Unfortunately, now there's going to be more terms coming about. Well, actually, some terms you can combine because from this you're going to get 1 times all of this. 2a cosine 2t minus 2b sine 2t plus t times the derivative of all that again. So what's that going to give me? So just derivative of that now.
Huh?
Derivative of all this in parentheses. Anybody?
Oh, you're asking?
Yes,
Okay.
I am asking. I'm always asking.
Minus 4a sine 2t minus 4b cosine 2t.
Yeah. Okay. So and these terms can be combined to give 4a cosine 2t minus 4b sine 2t. Okay. So finally, you can substitute all of these. Well, on the left side, we don't need the first derivative. It doesn't appear. We just needed it to get the second derivative. So yp double prime plus 4yp is going to be, so 4a cosine 2t minus 4b sine 2t plus t minus 4a sine 2t minus 4b cosine 2t, and then plus 4y. So plus 4t a sine 2t plus b cosine 2t. All of that must equal g of t, which is 3 sine 2t. Now, what really helpful simplification happens here?
I have a question.
Yeah.
How do we find a derivative? Did we just use the first derivative?
Yeah, because we needed the first derivative to get to the second
No,
derivative.
I'm saying, did you use it in this?
Not here, no.
Okay, I'm just
Yeah,
saying.
just because it didn't appear in the original DE.
The first and the third lines cancel each other. That's your road.
First and third?
Like the
Second and
4a cos.
No.
No, oh, shoot.
Okay, second and third.
Sorry.
Everything involving a T, those magically canceled out. So now we have to match these terms together. So we have 4a cosine 2t must equal 0 because there is no cosine 2t term over here. And then we have minus 4b sine 2t must equal 3 sine 2t. So similar to other examples where you match like powers of t on both sides, if you have cosines and sines or exponentials, you match those up too. So we get a is 0, and what is b? Yeah, minus 3/4 to make this whole coefficient of 3. So now you have your particular solution. Yp of t is minus 3/4 t cosine 2t. Okay. So, let's see. All right. So then your general solution. Y of t is your general solution for the homogeneous equation, which is c1 cosine 2t plus c2 sine 2t. And then you have minus your particular solution, minus 3/4 t cosine 2t. And then you determine these using your initial conditions. Okay. Now this is on, so this is page 61. I think I wrote that down earlier on the notes, so you can see how it is finished off to get all the coefficients. Try these out yourself. See if you use what's in the notes to see if you got them right. Forgot to make sense again. That works out well for many of you, for all of you who are not here. Last thing before you scram, on page 58 at the bottom, is a general case. How to get the form of yp of t. I thought it would be helpful to see specific examples during class, but now you can see all the rules, and we've seen examples of pretty much each one of them here today, but everything is covered in there. Know that chart. Now, it'll show up in the formula sheet too, but beware of it, use it for the homework. So that is your lifeline for determining coefficients. Okay, get out.